Good evening, all. Yeah, let's start this lesson. Coming to the lesson. Yesterday we discussed about the various classifications of chromatography. Today we are going to discuss about just checking my audible voice. Hello, right. Today we are going to today we are going to right discuss about the applications of chromatography. Applications of chromatography. Yeah, already we know that from the previous definitions. Chromatography is a full powerful tool for separation closely related chemical compounds. For example, if you have that 4 aminophenols or 2 aminophenols are these are the closely related. And then, that means only the position of substitution is different, but the structural organization is same. Position of the substitutions are changing. Okay, these kind of compounds are known as closely related compounds. Okay, such kind of compounds are occurred as a mixture of compounds. In such type of compositions, mixtures can be separated. Okay, for the separation, this chromatography is the powerful tool. Right. Next, chromatography is employed for qualitative identification and quantitative determination of the separated compounds. Suppose the mixture containing this kind of molecules as a mixture, right? Now, after separation, we can identify what compound it is. Suppose I have separated this mixture into 2 aminophenol and 4 aminophenol. After separation, whether these compounds are what type of compound or what is this compound? That is called identification of the compounds. And after separation, we know already the compound present in the mixture. We already know. If not known, or if it is the unknown compound, we find it what is that compound. After separation, after identification, and also we find the quantity of that compound. That is all. It is useful for the qualitative analysis as well as the quantitative analysis of a separated species. When you come into the qualitative analysis, when you come into the qualitative analysis, qualitative analysis, the qualitative analysis is widely used for recognition of the presence of or absence of a compound in a mixture. Presence of or absence of a compound in a mixture that contains a limited number of species in that mixture, whose identities are already known that can be identified very easily. Just comparisons. For example, I am running a chromatography that involving to identify the compound. Suppose I have conducted a reaction in the round bottom flask. I have conducted a reaction in a flask, right? That leads to produce reaction. The reaction leads to mixture of products. Mixture of products. How the products combination can be identified? Then, for this purpose, we are going to use a thin layer chromatography. A thin layer chromatography. In this, we are using A plus B are the starting materials, and C will be the product. After completion of the reaction, C will be the product. Now, here, just take any one of the or both. I'm taking A as a spot and B as the spot, and B and A both are the mixture along with the reaction mixture. If these are the A purest form, B purest form, and the mixture and reaction mixture, again the reaction mixture also loaded here. Now this is the A, this is the B, this is the mixture of this is the mixture of A plus B plus C. Now after we are running the chromatography, after we have run the chromatography in the mobile phase, now whenever we are running the chromatography in a perfect solvent, right? Suppose the A is moving here, B is moving here, and C is moving here, right? In the whatever the mixture also travel along with the mobile phase. The A will be here, the B will be here, and the C will be here. Now, in the comparison, just compare it. In the this is the reaction mixture, not the C. This is the reaction mixture. One, the reaction mixture only shows a single spot, that is the new compound, which is not matched with any A and B. Therefore, the such kind of PLC indicates that the reaction is completed. Reaction is completed, and a new compound is generated. New compound is generated. Right? This is the way we are going to use the chromatography in the qualitative manner. Qualitative manner. That is the same thing I am going to explain in the theoretical manner. Chromatography is widely used for the recognizing the presence or absence of the compound present in a mixture. Just look at this chromatography. We are just finding out whether that reaction is completed or not. Once we are observing the single spot, reaction is completed, only the product is shown, all the reactants are completed. Now, by using this chromatography, we simply identify that whether the A and B in a reaction are reacted completely or not. Just simply we are identified by using the chromatography. Okay. In a mixture that contains a limited number of species whose identities are known, for example, 30 or more amino acids in a protein hydrolysate can be detected by means of TLC and HPLC. Right? Not only for the simple reaction, we can also use it for the complex reaction and amino acid synthesis, amino acid sequencing, and DNA sequencing, RNA sequencing, such kind of procedures, we can also use the chromatographic methods. But in this method, in this qualitative methods, we can find out whether the given compound, whether the desired compound is present or not in the given mixture or not, right? However, the application of chromatography in identification of complex mixture of unknown composition is limited, because here we know that the A and B and C are we are already known. Suppose these A, B, and C are unknown, we cannot find whether this compound is so and so. But we can just identify that the compounds are there and how many compounds are there, but we don't know what are the compounds. That is the limitation is there. That is the application of the chromatography is identification of the complex mixture of unknown compound composition is limited, because the method does not give chemical composition or any molecular atomic spectra. The chromatography is the limited application. That limited application can give the information about that mixture containing how many number of compounds present. How many number of compounds are present. And if already known compounds are there, we can compare with the reference sample. Just final, simply we can find it. Suppose the mixture may contain the unknown compounds, it is very difficult. That means the chromatography will not use any molecular information or any spectral information. The spectral info, even if it produces the RF values, retardation factor values, that cannot be comparable with the unknown compounds. Therefore, it has the limited application. The limitation, however, has largely been overcome by the linking chromatography system to a detectors like UV, IR, mass, so that the separated compounds can be easily identified by using the detectors. Yeah, it is the advantage. Only simple chromatography will not give the any information regarding the molecular data. But whenever we are detecting the chromatography, not only all, not all cases, when simply we are using HPLC, GC, chromatography, we just separate the compounds. Then, whenever we are using the detector is connected with detector is like a UV spectroscopy, IR spectroscopy, mass spectroscopy, sometimes NMR spectroscopy also. Uh, can use the molecular information by which by the detector we can find out the compounds present in the mixture. Next, it is important to note that while a chromatography may not lead a positive identification of species in a sample mixture, it often provides sure evidence of the absence of species. Failure of sample to produce peak at some detection time as standard under similar chromatographic condition is strong evidence that compound in a question or in a mixture is about or presence at a concentration below detection limit of the procedure. This technique is thus widely used in sports field to detect absence or presence of banned drugs, steroids in the athletes. Okay, this is the qualitative application for the chromatography. Next, coming to the quantitative applications. What are the quantitative applications? Whenever we are separating the compounds, whenever we are separating the compounds from the mixture, whatever the given mixture, whether it is a reaction mixture, whether it is giving a natural mixture obtained from the natural products like plants, soil, or some others. After identification of the compound, we are going to separate it. After separation, those compounds will be quantified. That means that the results obtained in the numerical data, whether it is in grams, milligrams, or concentration scale, that is called as quantitative application. Important use of chromatography lies in its quantitative applications. These quantitative applications of the chromatography is very important. After separation of the chromatography, after separation of the compounds, or after recording the chromatograph, that provides the information on the amount of separated species present in the sample. Understand? Suppose if you are separating the compounds, that is one type. Separation of the compound will get the individual compounds. Or some chromatographic methods, we are running the sample through the stationary phase by using the mobile phase. We are record the chromatogram by using the chromatograph. After analyzing that chromatograph, we can find out how many number of compounds present in it. After finding out the different compounds, based on that chromatograph, we can quantify the amount of the compounds present in it. Okay, the separated components peak height and peak area can be compared with that of the standard peak height and peak area. Suppose here one of the chromatography recorded, some of the chromatography is recorded. Now the recording like this, it will use the broad peaks and like that, some peaks like this. Right, based on the peak height and based on the peak area, this will be compared with the standard one, and comparing with the standard one, then They are finding out the amount of the compound present in the mixture, right? As defined earlier, a chromatograph does shows several peaks of separated components. The quantitative analysis of the separated components can be made using the peak height and peak area. Okay, just by comparing the peak height and peak width or peak area with the reference chromatogram, by simply we can find out the amount of whether first we can identify the compound and later we can finding out the quantity of that compound present in the mixture. Next, analysis based on the peak height. Analysis is based on the peak height. The height of the chromatographic peak is obtained. Look at here. Just I have given the this is the spectra. This is the chromatograph. This is the chromatograph. This peak indicates the one component. This peak indicates one compound. This peak indicates the one compound. This peak indicates the one compound. The height of the chromatographic peak is obtained by connecting the baseline. This is the baseline. Simply, a baseline means constantly moving. This is recorded in the MT chromatograph, the chromatography instrument that gives the this base peak, right? The height of the chromatographic peak is obtained by connecting the baseline on two sides of the peak by a straight line and measure the perpendicular distance. Here I am showing like this. Just see that. This is the peak, a recorded peak. Now, when you observe this, the height of the chromatographic peak is obtained by connecting the baseline. This is the baseline, right? This is the baseline which is connecting. This is the highest peak area. Now, baseline on the two sides of the peak. Now, here I am written one line. This is the one. The distance between these two is called peak height. That is called peak height, right? Straight line and measuring the perpendicular distance from the line of the peak. Now, whenever we are measuring this line, that is called peak height. This measurement gives the accurate results provided chromatographic conditions do not alter peak width during sample and standard development. Right? Whenever we are running any sample, we are the chromatography instrument is developed or running the similar conditions, the same compound at any time gives the same peak in the chromatograph. Okay, that kind of standardness that can be maintained. Analysis based on the peak area. Analysis based on the peak area. Next one is analysis based on the peak area. Analysis based on peak area, right? If conditions are not controlled, suppose temperature, flow rate, pressure, size of the stationary granule size, particle size of the stationary phase, and different kinds of nature of the stationary phase, nature of the compounds, nature of the mixture, nature of the mobile phase. These are the conditions. If conditions are not controlled, if any one condition is changed, the chromatograph may show broad peaks, sometimes broad peaks, sometimes height, more height peaks, sometimes the high width peaks. Okay, that difference can be easily observed. Under such conditions, it is better to measure when peak area than the peak height. Suppose if you are when you are maintaining well-controlled spectrum chromatogram, then you can get the peak where you need to only consider peak height. But if we are unable to maintain the conditions of the experiment, then you need to maintain the peak area, then the peak height. Because peak area is independent of the broadening effects. Peak area is the independent of the broadening effects. If peak broadening occurs, then peak height may change, but peak area remains the same. That is the thing happen. Most chromatographic instruments are equipped with electronic integrators that provide measurement of peak area. Okay, most instruments are manufactured in such a way that they are integrated, some electronic integrator that provides the measurement of peak area. Different methods by which quantitative analysis by chromatography can be carried out. One, those are A. Calibration method using the external standard. Calibration method using external standard. External standard. Right. Next, B. Inst Yeah, sorry, due to rain, power interruption is there. Okay, again, I'm starting with my mobile. There, right. Different methods by which quantitative analysis by chromatography can be carried out. The first one is the calibration method, and the second one is the internal standard method, internal standard method, and third one is the area normalization method. Area normalization method. When you come into the first one, external standard, calibration calibration using external standard, external standard. Now, this method is similar to the other calibration methods using external standard. Series of standard solutions of the same component. Suppose if you are making the different solutions with the from lower concentration to higher concentration solutions, higher concentration solution. You are making suppose 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10 different concentrated solution. It is the increasing order of concentration, right? that series of standard solution with the same composition of unknown sample are prepared. Chromatograms of these standard solutions are obtained. Each solution you make the chromatogram. Each sample gives one chromatogram. Chromatograph 1, chromatograph 2, up to chromatograph 10. Right? The peak, height, and area are plotted as function of concentration. You may take the peak height or peak area. Suppose if we take the first one is here peak height versus concentration of the sample. We have the 10 samples are there. There's one concentration versus peak area, peak height. You make a graph that is passing through origin. One first sample, second sample, third sample, fourth sample, fifth sample, sixth sample, seventh sample, 18, 9, like 10. A straight line will be up, right? Similarly, if you take the peak area, peak area versus concentration, here also it gives the same peak, right? We can get the two kinds of peaks, two kinds of graphs, right? Linearly is proved with the line of plot passing through the origin. Here both the cases that line is passing through, linear line is passing through the origin. Chromatograph of sample mixture is obtained and its peak area or height of separated compounds is calculated. From the peak height and peak area, the unknown concentration of the component is determined by extrapolation. Suppose if you are recording the sample mixture, that sample mixture contains the unknown concentration of the compounds, then one of the compound concentration is peak area is matched here. Then just extrapolate it, that is matched to at one place of the peak area, then again extrapolate it with the concentration. Therefore, this peak area matches to this concentration. Similarly, if any other compound peak area is like this, that will be matches to here, right? Once you are constructing the standard or calibration plot, then we can find out the concentration of the components present in the mixture, right? This is the calibration method. Next, coming to uh, internal standard method. Internal standard method. Second one is internal standard method. Internal standard method. What's happening in this method? This method is also similar to the internal standard method as described earlier in other instruments like potentiometer, colorimeter, like this experiment. Okay, this method gives the highest precision because the effects of different variables are removed by this method. In this method, a fixed known quantity of internal standard is added to both standard and sample mixture. The ratio of the standard peak height or area to standard peak height or area is measured. Plots of these ratios against the function of concentration of the analyte is obtained. Linearity of the plot through origin is established. Unknown concentration is determined by extrapolation of the standard graph. For this method, it is necessary the internal standard peak must be well separated from the peaks of all other components in the sample. But it must appear close to the analyte peak, whatever the analyzing peak or what we are going to consider the peak, it must be appear to the analytic peak. Right? Next, third one is area normalization method. Area normalization method. Area normalization method. Right. The effects of different variables are avoided by this method also. Whatever the internal standard we are taking, we are recording the recorded the chromatogram, by which we can compare the area or height of the peak obtained, which is compared with the compounds present in the mixture. That is the internal standard. But in the area normalization, here also we can control the several variables that are avoiding the avoided by this method. Complete solution of all components of the sample mixture is done. The areas of all eluted peaks are computed. Correction factor for differences in detector respond to different compound type is applied. The concentrations of analyte is obtained by ratio of peak area to total area of all peaks. Okay, by taking this difference, we can normalize the peaks. After normalizing the peak, we can identify the compounds. Next. Next, coming to the next lesson. Today's, when we are going to specified unit, that is principles and techniques of paper chromatography. Principles and techniques of paper chromatography is unit 9. Chromatography, paper chromatography. Right. What the topics we are in this unit going to cover? Principles of paper chromatography, types of paper chromatography, techniques of paper chromatography, applications of paper chromatography, advantages and limitations of paper chromatography. Now coming to the introduction to the paper chromatography. Paper chromatography is a simple form of two-dimensional chromatographic method that has now become an extremely valuable analytical tool to organic chemists and biochemists. Um, Conbean is the first to introduce the paper chromatography, but all credit for making paper chromatography a popular technique goes to Cambridge School of Workers, Martin and his co-workers. Cellulose filter paper is commonly used as stationary phase in paper chromatography, with wide variety of solvents as used as the mobile phase. Paper chromatography is regarded as partition chromatography, where stationary phase is water held immobile by adsorbing an cellulose molecule of cellulose filter paper. Paper chromatography has a wide and versatile field of applications. Paper chromatography was originally used to separate organic mixtures and amino acids. It was later adapted to separate and identify a variety of substances, including inorganic, ionic, and ions and cations anions and cations. It is used in almost all areas to solve complicated problems in chemistry, biology, biochemistry, and and so on. And it has an advantage of being simple, rapid, and inexpensive technique, and with high separation efficiency. This is the highest advantage of paper chromatography. In the paper chromatography, we are just using the a cellulose strip. That cellulose strip acts as a mobile phase. After cellulose strip is submerged in the water, therefore we can use the wide variety of mobile phases. That wide variety of mobile phases are liquid. The liquid mobile phase is moving from down to top when the compound is partitioned between the water and mobile phase. The water is adsorbed on the cellulose phase. Okay, the compound is partitioned between the water, sorry, the compound is partitioned between the water and mobile phase. Therefore, that is the reason we call it as partition chromatography, and it is a inexpensive chromatographic method. Now coming to the principle of paper chromatography. Paper chromatography or any other chromatography has basic principle is same. Basic principle is same. Principle of paper chromatography. In this, the principle behind separation mixture by paper chromatography can be explained based on the partition behavior, capillary action, and migration parameters. These three factors are important. One is the partition behavior, capillary action, migration parameter. When you come into the partition and capillary action. Paper chromatography is regarded as a type of partition chromatography. Already previously I'm given the knowledge on that. Right. The stationary phase is usually water that is held immobile in fibers of paper. Paper used in cellulose filter paper. Paper used in this chromatography is cellulose filter paper. The mobile phase is usually an organic solvent, or any other ionic solvent, and any other solvents, aqueous solvents. Okay, this is called as normal phase paper chromatography. Non-normal phase paper chromatography. Non-polar liquids like silicones or paraffin oils can replace water in fibers of the paper of cellulose by suitable treatment of paper. In such case, the stationary phase is the non-polar liquid held immobile in pores of the paper. The mobile phase used will be a polar system or any aqueous alcoholic based solvent system. This type is called as reverse phase paper chromatography. Again, I am repeating, the mobile phase used will be a polar system or any aqueous or alcoholic based solvent system. This type of chromatography is called as a reverse phase paper chromatography. In either case, components of mixture to be separated by the partition between liquid held in the immobile in stationary phase and the mobile liquid phase. The mobile phase moves on paper by capillary action. The mobile phase moves on the paper by capillary action, and there is a separation due to difference in the rate of migration of the compounds or components. As a result, the separation or the separated components appear as different spots or bands or zones on a paper. Right? Due to the capillary action, mobile phase is moving on the stationary phase. During the movement, the components present in the mixture is partitioned or distributed between the moving phase and stationary phase. That is the reason the separated compounds appear as a different spots, bands, zones on a paper. Cellulose filter papers are normally used as support for stationary phase. However, modified papers with a different material can also be used as the support for stationary phase in the paper chromatography. Cellulose materials and modified papers, because of their structure, can also play a role of adsorption, ionic exchange interactions in the paper chromatography. Partition adsorption or ion exchange may play a major role in causing separation depending upon condition employed for the analysis. We can apply the several conditions. Based on that condition, either partition or distribution or ion exchange may play a major role in causing the separation of the components present in the mixture. Paper chromatography, as discussed in earlier, it is classified under, it is supported in the force of paper, and the mobile phase is moving through the stationary phase by capillary action, or under the influence of the gravity, or under the influence of gravity. The general principle of chromatography, that is distribution coefficient K and selectivity factor alpha, are also applicable to paper chromatography. Again, I am repeating, the general principle of chromatography is applicable to the all chromatographic methods. Similarly, here also it is applicable to the this paper chromatography, by which distribution coefficient and the selective factor are also applicable for the paper chromatography. Migration parameter. What are the migration parameter? Just what are the parameters which are influenced the migration of mobile phase and migration of components, or migration rate, are called as the migration parameters. Any factor that influences the migration or moving or movement of components present in the mixture is called migration parameter. The movement of substances relative to the solvent is expressed in terms of migration parameter RF, RX, and RM. RF, RX, and RM. These terms indicates the position of these terms indicates the RF, or rate retardation factor, Rx, you can also call Rm. These terms indicates the position of migrated spot on chromatogram and help in quantitative or qualitative characterization of the substance. Retardation factor is, this is Rf, retardation factor. Retardation factor. It can be calculated by the equation, Rf is equal to distance traveled by the compound or substance from the origin origin line divided by distance traveled by the solvent from the origin. Okay. By using this equation, we can calculate the RF value for the each components present in the mixture. Then, how this can be calculated? I will show the. Suppose this is the paper chromatography. This is the paper which is used as a support for the immobile stationary phase, which is coated with the water, and also after running, this is the origin line. Means in that on origin line we are loading the compounds. After loading the compounds, we are running the chromatography or developing the chromatography in a development tank. This is the development tank, right? We need to take the solvent, suitable solvent, any organic, polar or non-polar solvent. Now it is starting moving slowly from the down to up. Okay. After development, you take out this slide from the development tank. Right. This is the origin line. The compound is moving here, and another one, suppose this is the mixture, it contains the one compound, and this is containing another compound. This is the mixture, this is the pure compound for standard reference. Now, what is the RF value? This is the compound A, this is the compound B. Now, solvent is moving to this up to this distance. Now, the distance between the distance traveled by the solvent from the origin is taken as a D. The distance traveled by the components present in the mixture is taken as E. The distance traveled by the compound, another compound, this is the compound A. This is taken as F. Now, RF of RF of A is equal to the distance traveled by the components or substance from the origin is F, and the distance traveled by the solvent from the origin to the solvent front is called, this is called solvent front, where the maximum range, maximum distance traveled by the solvent is called solvent front. That is D. That is RF value of A is equal to F by D. That gives the unitless value. That is called RF value. Similarly, RF of E is equal to RF of the compound E equal to, what is that? The distance traveled by the compound B is E, and the distance traveled by the solvent from this origin to solvent front is D. Now this is called RF values of compound. By this way you can calculate the RF value of the compound. Next, RF is the function of distribution coefficient. It is constant for a given substance provided conditions of chromatographic system are kept constant. Whenever we are maintaining the controlled conditions, RF values are always constant. If you change the conditions of chromatography, therefore the RF values are also changed. Some of the factors that influences the uh, RF value, some of the factors that are influences the RF value is first factors affecting the RF values. Values. First one is mobile phase. You change the mobile phase, RF value change, and its compound composition. Sometimes you are using the same mobile phase, but composition change. Therefore, RF value is also changed. Second one, quantity of the mixture, quality and nature of the solvent used. Quality and nature of solvent used. That means if nature is changed, the retardation also changes. Therefore, once the retardation changes, the retardation factor is also changed. Quality, if it is the more highly pure, the solvent is always gives the accurate results. If it is not a pure, it is somewhat it is contaminated with other substances. Therefore, RF values are also becomes change. Next, distance traveled, distance the origin which the mobile phase is allowed to run. Suppose here in the previous case, I have used this chromatographic plate. Whenever I'm developing this chromatography plate, sometimes I'm running from origin to here. Sometimes maybe I'm running from here to here. That means the distance increasing, the RF values are also increasing. Therefore, while you are developing the chromatography or paper chromatography, you need to maintain the origin to solvent front position from distance. Then only you can get the accurate RF values that will not change. If you are changing the distance from the origin to solvent front, that is also changes. Right? Next one, amount of the mobile phase in the reservoir. Suppose in the beaker, if you are one time we are using 1 ml, second time we are using 2 ml, third time we are using 2.5. Therefore, if the solvent availability is increasing, therefore the mobile phase is also moving fast. Sometimes it travels fast to from the down to top. Therefore, if you are, it is also depends on the amount of the mobile phase in the reservoir. And uneven solvent migration. Sometimes, if you are placing the plate unevenly in the development tank, the solvent may moving in unevenly. Therefore, a zigzag manner, the solvent may be moving from the top down to top, from margin to the solvent plate. That is also leading to the difference in the RF values. Similarly, concentration of the sample and the impurities of the salts present in the sample. Whenever we are preparing various salts, one time we are preparing one composition, the second time we may be prepare the sample mixture in this different composition. Therefore, the composition of the mixture is changed. RF values are also changed. And sometimes the components are different from the second time prepared composition. Once the change of the composition is occurred, the RF values becomes changed. Next, medium used for the separation. Medium used for the separation. Whatever the medium, suppose if you are using the compound mixture preparation, in the one case is the chloroform and another case is the methanol. That is also affects the separation. Therefore, RF values are also influenced. Quality of the paper and direction of the fiber also important for the paper chromatography. Whenever we are choosing the paper, you need to check the quality, whether the quality is similar to the previous one or not, or identical to previous one or not. We need to verify it. Then only we can run the paper chromatography. Otherwise, the RF values becomes altered. And we need to check the fiber direction. We know that whenever they are making the cellulose filter papers, they are using the cellulose fibers. The cellulose fibers may be sometimes one direction, sometimes another direction. Therefore, whenever we are making the cellulose paper and use that paper in uniform direction only, the fiber should be only one direction should be maintained. Then only you can get the RF value same. Method of development, duration and the direction of the development, the temperature of the system, size of the container in which the experiment is performed. All these level factors can influence the RF values of the paper chromatography. Okay, RF values of two different components are different for a given system. If you take the mixture that is having two components, the two components are having different RF values. There is no comparison. It should be noted that RF values are not contained under every condition. The values will be vary with the experimental conditions used. Hence, the experimental conditions should be reported along with the RF values. Okay, we cannot control the reaction conditions, and we cannot to change the reaction condition. If change the reaction condition, we cannot get the result product. That's why you don't need to change the reaction conditions. We no need to change the reaction factor. That's then whenever you are reporting the RF values, you need to mention the reaction conditions.